for any p of x, we know it uniquely factorizes into something like this: a n times x minus alpha I. I run from something like 1 to n, and then we know q is similar like bn. The product I like n. This is x minus beta I. And then therefore this any functions in this would be f would be something like this. Then f would just be an over bn with some product of x minus alpha to some exponent e to the I, and then I run from 1 to k. Make sense? So we have those similarities, right? So in some sense, this functional field C join x is very similar to the field rational numbers. So, but what else can we do actually in this field? Is that we can actually, for example, consider functions, something like function, I don't know, we can consider the Taylor extension at 0, for example. Right? We can consider the Taylor extension, which is I run from 0 to infinity. So for any functions in C with a free variable x, that field, we know it can uniquely, it can be for any point we can find the Taylor expansion, right? So, but we can't really do that for Q, can we? Not really. You can't Taylor expand Q, right? So what we want to do is we want to find a method. So this is a method. So for example, for that functions, right? We have x tends to infinity, so x equals 1, and then x to the infinity 0. Right? But for any x, we know that we can use this polynomial to study the local behavior of this function. So we also want to replicate this result to study local behaviors of the rational numbers, and that's why we actually try to introduce the p-adic numbers. So okay. So to begin with, we just try to write our numbers something look like a Taylor polynomial. So we can actually sort of achieve this. That's what you read. We actually can try to achieve this through actually just base 10 representation, right? So what I'm trying to say. So for example, we just take any number. For example, 2, 3, 7. So this number can be written as 7 times 10 to the 0 plus 3 times 10 to the 1 plus 2 times 10 to the 2, right? This is just the base 10 representation of this number. So this number starts to sort of look like a Taylor polynomial already. Although it's not infinite because the other coefficients are 0, but we actually try to achieve something like that. The only problem is 10 is not a prime, but this factor is a prime element. This is sort of behave like prime in this polynomial ring. So this is like a prime in this, but 10 is not a prime. But that's not a big deal because we have the base p representation, right? So we try to find the base p representation. For example, we can just take base 7 representation. So we can try base 7, for example. We can try base 7 of what? Of this number, 320. Can someone tell me what is the base 7 representation of this number? Okay, it's kind of hard. Okay, that's fine. I'll just write down the answer for now. It's 5 plus 3 times 7 plus 6 times 7 squared. Okay, so it starts to looks closer, right? Looks sort of closer to a Taylor expansion of a polynomial. So now what are we doing? So let's explain how do we get this, right? How do we get this is actually through division with remainder theorem. So first we divide by 320 by 7. So 320 is equal to some number times 7 plus a remainder. And that is 45 times 7 plus 5. And that's how we get this 5. Make sense? We just do division with remainder on this number. And now we do division with remainder on this number, 45. So 45 is equals to 6 times 7 plus 3. That's how we got the 3 here. Let's call this this. And then we just have 6, and 6 is 0 times 7 plus 6. So that's just the 6. Okay, so we sort of know how to write. Essentially, we are able to write any integers, or at least positive integers. So for any positive, so what do we know? For any positive integers, this is strictly positive. We are able to write n that looks something like alpha I p to the I from 0 to some number n, right? We have this is just the base p expansion. Good. Now we're trying to. Or try another. Well, let's try another. Let's try another number. Try another number. Is this what I wanted? Let's try another number. Let's try another number. So we want to try. I want to try 72 and base 3. So what should we? How do we get the base 3 representation of 72? We'll do long division, right? We'll do division with remainder. So 72 equals how much? Something times 7 times 3 plus something. And actually, let's see. So 24, right? This is 0. And now we do 24 equals something times 3 plus something. So 8 times 3 plus 0, right? And now I have 8 is something times 3 plus something. This should be 2 and 2. And then 2 is something times 3 plus something. This has to be 0 and this has to be 2. Therefore, 73 is exactly 2200 in base 3. But actually, this starts to tell us something about the local information of the prime 3. Because this number has exactly, so you know, 3 squared is the highest power of 3 that exactly divides 72. And why do we know it's 2 here? Because we have 2 zeros here. So this base P expansion is actually telling us something about the local behavior of a number at the prime P. But what we can do? But we can do actually much better in the complex analogy. Let's consider a function. Let's consider the function. Let's consider the function f of x equals x over x minus 1. So we can try to. So first we can expand at 0, obviously. So we can try to expand at 0. Find the Taylor point, expand at 0. Then what do we have? We can just use the classical trick. Just do this. 1 over x minus 1, where this is 1 plus 1 over x minus 1, right? And this one you can use the geometric series. So this eventually should give you. If you expand this by geometric series, you would just get negative x minus x squared minus x cubed, etc. That's good. But we can actually do something interesting in the complex analogy. So what we can do is actually, we can also find the Lorentz series at x equals 1. What does it mean is we can actually, so for Taylor series, we only allow positive exponents. The Lorentz series, we also allow negative exponents. So this could also expand at x equals 1 by letting this minus this. It's just same trick. You just have this number to the negative 1 exponent plus 1. So we also want to replicate something like this in the real and the rational case, right? Because we want to study local behavior, and the Lorentz series is a way we study local behavior for a number at the pole, for a rational function at the pole, right? So now we try to achieve this by guessing, apparently. So let's guess something. Let's guess. See how should this work. Well, the first example is fairly easy. The first example is just 320 over 49. We're going to expand at base 7. Or let's say base 7. Let's say 7-adic. We're getting to the adic. So that's 7-adic. 7 just means we try to expand sort of like base 7. Right? So this is not that bad because we just know the expansion of 320 is, you recall, what do we know? I remember. Can't remember. What do we know? We know, okay. We know okay, this is, how much do we have? 320 is 5 plus 3 times 7 plus 6 times 7 squared, right? That's what we did a few minutes ago. And now we try to expand this. We try to expand that in 7-adic. But what we can do is we just can divide by 7 squared both sides because 49 is 7 squared. Therefore 720 over 49 is just 5 times 7 to the negative 2 plus 3 times 7 to the negative 1 plus 6. Or equivalently, 720 over 49 has base a 7-adic representation, 6 dots 5 3 5. So divided by number that is power of p is 5 because we can just shift the decimal, the same as the usual way. But how about something else? Let's try something else. Let's try to expand. Let's try to expand a half in 5-adic. Let's try a half. Let's try a half. So we tried a half in 5-adic. So what is a half in 5-adic? We don't know how to do it, do we? There's no obvious way. So what do we try? We try long division. Surprisingly, we try long division. So how do we do long division? Very interesting way. The steps. We let a half be equals to 5 because we still want 5 because that's 5-adic. So we want 5 times something. Well, 5 times something plus something. And this number should be 0, 1, 2, 3, 4, right? And this number, because we have a half, we maybe just guess we can also allow, something with a half with 2 on the denominator. So it turns out we can actually do this. So this time this plus 3, right? Yes. So I have 3 here. That's good. So we try division with remainder theorem again. So half is how much times 5 times something plus something, and turns out we should have another 5 here. Sorry, another negative half here, right? Because there's a negative and a negative here, and then you got a plus 2, and then we have then you have a negative half again, which is just repeating this procedure. And if you remember, this is a unit digit. This is tens digit. This is hundredths digit. So actually, this number, if we just believe whatever we did is right, this number should have 5-adic representation that is 3, 2, 2, 2, 2, go all the way down to this side. Not that side, but this side. So this has an infinite long integer representation going to the left, which is very interesting. It doesn't really make any sense, does it? But let's try if this number is actually the inverse of 2 in our a 5-adic representation. How do we do it? Well, let's just multiply this 5-adic representation. Let's say this is 5-adic. Let's multiply this 5-adic representation by 5. Just multiply this number by 5. So I have 3, 2, 2, 2, 2, 2. Infinite of 2 this side, okay? So 3 times, 2 times 3 is 6. 6 is 5 plus 1, so I have 1 here, and then this is 5, so it's 1 here. 2 times 2 is 4. 4 plus 1 is 5, so it's 0. You have 1 carry on. 0, 0, 0, 0, 0. The infinite 0 going to the left, so this number is actually 1. Right? Because, you know, it's like 1, all zeros on this side, so it's got to be 1. Maybe it makes sense, but, you know, maybe. We just say maybe it makes sense. So right now, it looks like it sort of works in some sense. So actually, let's try another number and see how it works. Should I try another number or switch? 606. Okay, let's now try another fraction. You can just assume you can just believe me, all fractions should work this way. Let's try another more interesting. So what do we have? So if you trust me, we know we can represent all x in Q positive, including 0. We can represent all this in 5-adic, so in P-adic. So we can represent all this in P-adic. So this is good. Now the only problem is we need negative numbers. In P-adic system, you are not to just add a negative sign. We'll see how it works. So let's consider how do we calculate the negative 1 in 7-adic number. So the claim is the number should be negative 1 should be just infinite number of 6 to the left. Why? Let's do the math. See if this is the inverse of 1. We're gonna add infinite number of 6 this side, right? Infinite number of 6 this side, and then we add 6 here, and then 1. Okay. So 6 plus 1 is 0. 7, carry on. 0, 0, 0, 0, 0, 0, infinite to the left. So we know this is right. Although whatever this means doesn't make sense, but it seems to be right. You can still do addition, multiplication, division, subtraction, whatever you want, right? So it should be like a few. But what does it mean? How does this make sense? Well, how does it make sense? It really depends. Like, let's think about why does a decimal representation of a real number make sense? Let's suppose you have a number which is a decimal representation. Suppose you have a number that has a representation something like an minus 1, all the way a0, and you have decimal point here, and you have a negative 1, and you have infinite to that side. This is saying x is the limit of the sum, right? This infinite sum of n I from n all the way to negative infinity of ai 10 to the I. Well, the reason this sum converges because eventually go that side. This 10 to the I, this is actually this is negative, so it should be like 1 over 10 to the very large number, and this goes to 0, right? This goes to 0. K goes to infinity. So the reason this makes sense is because we use a sequential definition for our decimal representation, and the series converges. But this doesn't really make sense because how could p to the n converges? Like this obviously goes to what? This diverges to infinity, right? Because we are trying to find infinite number of digits to the left, not to the right. So this 100% diverges. How do we fix the problem? Well, let's think about what do we mean by convergence. The convergence is defined by topology, right? If you know what a topology is. Or in some sense, we define by distance. We define by distance. So if you know your analysis, you know a sequence is normally something like let's say the convergence of sequences x to the n goes to x. Can someone tell me what do we mean by sequence convergence? So for every epsilon greater than 0, every epsilon greater than 0. there exists n, such there exists n such that n greater than n implies x to the n minus x plus n. So that's good. That's good. So, but the trick is this. So what do we mean by this? So the trick is, what do we mean by this? This is absolute value, right? So maybe we can fix up the problem by redefining absolute value. Maybe. I'm just saying maybe. Maybe it's very interesting. So how do we fix the problem by redefining absolute value? So the problem is you never learned what the absolute value is. Let's define what absolute value is supposed to look like. So basically, we are redefining everything. Now that's the goal. That's the goal. So absolute value. On a field K. Okay, you can think K is Q. Like this, think K is Q. So we have
just make it Q.
No, make it K.
Don't make it K. Make it Q.
Fine. Let's call it F. How about F?
Yeah.
F. You can say F equals Q if you want. So the function is something that defined from F. Takes number in F. But so we want to map to something like R positive, R non-negative, right? We want absolute value to be non-negative. Good. So that's the first one. The second one is this is always greater than 0, and the equality if and only if x equals the zero element in the field F, or the 0 in Q if you want. The next one is we want the absolute value to be multiplicative. This should be the same as evaluate. So x times y, take absolute value should be the same as x, absolute value, y absolute value, right? The last one is what we always want is triangle inequality. So that's our definition of absolute value. Good? So example. You can check R with the usual absolute value is a field with absolute value. So example. Another example is R, and we take absolute value to be the trivial absolute value. So we take any element, x equals 0 if x is 0, and 1 if x is not 0. This is also absolute value, if you want to check. And that generates a trivial topology, so nobody cares, basically. That's too trivial. And now once we have an absolute value satisfy this, you can see we can induce a metric. We have an induced metric. How do we get the metric? Well, I assume you guys know what a metric space is, right? Good? A metric space is good? Okay, metric space is good. So in this metric is d of x, y. So we basically try to define distance. We want to define distance be the difference between the.
I don't know what a metric space is. Could you explain it in intuitive terms?
It's a way to measure, how I measure distance. That's a metric,
No, but what's a metric space? Could you intuitively tell me what a metric space is?
It's a set with a metric function. Good? You're happy?
Okay, I'm happy.
Okay, good.
Chris,
So,
can the distance ever be infinite?
Yes.
Yes.
No. Now in metric, we'll see. No, never. Of course, never. Okay. Now let's try to fix our problem by redefining absolute value. So before we redefine absolute value, I want to define a valuation. Now we have a definition. Okay, let's just define a valuation directly. So let's define the P-adic valuation. We have better choice. Let's define the P-adic valuation. So we denote the valuation by nu p of x. Let's first define the valuation on z. So let's let x in z. Let's take a integer. We define valuation of x to be a. That's nonsense. Where a is the largest natural number such that p to the a divides x. Make sense? We want to find the largest number of p that divides x. Let's just chalk that because those are fancier chalk. I think they don't. So let's have an example. Example. 5-adic valuation of 25 is 2. Because why? Because 5 squared divides 25, and 5 cubed is too large. It does not divide. Make sense? We have the p-adic valuation on integers. I'll extend the p-adic valuation on Q. Let's extend the p-adic valuation on Q. Should I write? Let's erase this. Basically, for the absolute value, you just assume whatever absolute value should work. Pretty much works. So now we define the p-adic valuation. So for any x in Q, we write x as A over B. So we define the valuation, the p-adic valuation of x, to be the valuation of p at A, subtract the valuation of p at B. Good? Now you can verify, and we further define, because there's a problem. 0 is a problem. You see, the 0 has too many 5s dividing. Like, 5 to any number is a divisor of 0, so it's not good. Like, it's a divisor of 0, right? So we're gonna define the valuation of 0 too. So we let the p-adic valuation of 0, as you can guess, to be infinity. And therefore, let's check some properties. I don't think I have the time to check, but I'll just list the properties. Now some properties. So first, p-adic valuation of x equals infinity if only if x is 0. The second, valuation is multiplicative. I'm sorry, it's additive. So this equals p-adic valuation of x plus p-adic valuation of y. And the third one, you need to do something like number theory to verify this x plus y is at least the minimum of valuation of x valuation. From evaluation, we define an absolute value, the p-adic absolute value. Let's go this way. Let's define the p-adic absolute value. Let's define p-adic. This is the most important part. So we define the absolute value of the p-adic absolute value. We write x of p. By definition, p to the negative valuation of p at x. You can actually verify this is indeed an absolute value that satisfies the property by using the convention that p to the negative infinity is 0. And further, actually, it's even better than a normal absolute value because it satisfies a stronger form of the triangle inequality. You actually have x plus y of p value, p-adic absolute value is actually less or equal than the maximum of xp comma yp. This is called stronger triangle inequality, and metric something like this called ultra metric. This is interesting, but what are we leading to? Like, what are we doing here? So let's prove something actually sounds interesting. The first claim is all triangles are isosceles. So the claim 1. Do we have the time to prove it? I don't think. Okay, let's prove. So I'll just write some propositions by proving this. So all triangles proof. So okay, let's see the proof. The proof is actually fairly easy if you assume the stronger triangle inequality. So first we assume, so basically we have points. So to prove this, we'll just prove the following proposition, or just enough to show. We'll show this proposition. If x is not y, this implies x plus y is equals to maxima of x and y. So why is this true? So suppose you have a triangle something like x, and you have another y, and x plus y would be this guy, right? This is the x plus y. So if x equals y, then this is isosceles, and we're down. If it's not x equals y, then this guy is equals to this or this. So it's isosceles anyway. So all triangles are isosceles. How do we show this? So without loss of generality, we assume x is actually smaller or larger. Let's assume x is strictly larger than y. Then by strong triangle inequality, we have x plus y is less or equal than x, because this is less equal than the max of those. That has to be x. And further, we have x is less or equal than the max of x plus y, comma negative y, because negative y plus y plus negative y is x. So that's the strong triangle inequality. But this guy is the same as y. The y is less than x by assumption, so this has to be x plus y. Therefore, x is x plus y, and we're there. And that's very good. Now we know all triangles are isosceles. The consequence of this is also pretty cool. The consequence of this is that you can verify all closed laws are open. The closed laws are open, so they are open laws, and all open laws are closed. Well, I mean, okay, the closed laws are closed, and the closed laws are also open. That's a clear. So, in some sense, this looks like a Cantor clock. It's very discrete. It's very disconnected in this space. And now we can talk about sequences eventually. So, as you can see, under this P-adic valuation, p to the n, under this valuation will be just p to the negative n, which tends to 0 as n goes to infinity. So we solve the problem of the P-adic representation not converging. We're good, in some sense. Now we want to talk about Cauchy sequences. Do you guys know Cauchy sequences? Okay, let's talk about Cauchy. What time is it? I think. Let me finish. At least I need to construct P-adic numbers. The Cauchy sequences. So a sequence A sub n is Cauchy if for every epsilon there exists n such that they're close eventually to each other, not to a limit point, but to each other. So it's for all m n greater than n, x m subtract x n is less than epsilon. So that's our definition of a Cauchy sequence. There's a problem with Cauchy sequences here, is that Q under this norm is not complete, which is the same as R under Q under the normal. The R norm is not complete because you have pi, which is not in Q, but it's a Cauchy sequence of 3.14, etc. Right? So we try to fill the holes, and guess what? You can fill the holes by completing the field, by filling all the holes. So how do we fill the holes? We use a process called completion. Have you guys ever encountered completion? I hope so. If not, let's see. So we can make a, so now we can define the p-adic numbers, which is QP, be the completion of Q with respect to this p-adic norm. So that's the definition of p-adic number. If you ever see QP, that's the p-adic numbers. That's completion of all this. That's what it's saying. That's basically we try to find a larger space bigger than Q, such that all Cauchy sequences converge to some sequence. Good. So how to construct? I don't have time to do it. But I can give you a general idea. Basically, you consider all the Cauchy sequences. Consider all. Basically this, such that this is Cauchy. And then you want to build an equivalency relationship on this if they are closed. If xn, if xn and ym are closed, sorry, yn are closed, are equivalent, basically are closed, right? Well, closed. Are closed if the difference goes to 0. If the difference goes to 0. And basically you have an equivalence relationship, and you can show this is a metric, and you can further show it's a field. If you know algebra, you can consider the product of Q. We take the big product with respect to n, which gives you a ring. And you can verify the ideal of all null sequences, of null sequences. This is a maximum ideal, and then you consider this is a ring R, and then we take the R modulo the maximum ideal. By your algebra, this is a field, and this is called p-adic field, QP, right? We can also do this low-key method or whatever. And then we are saying Q is actually embedded by injecting Q. Okay, now we can inject Q into QP. So the claim is here, you can always inject Q into QP. If you remember, the QP construction is always some infinite sequence, right? This is my construction, let's say it's R modulo I. Then I inject any number Q, just map to the constant sequence X. And that would give you an injection into QP, which is good. And there's a very interesting, so in real analysis, you probably heard of a term test for divergence. So suppose you have a sequence AN. Suppose you have a series AN from 0 to infinity. This series divergent if the absolute value of AN not equal to 0. But in p-adic case, the converse is also true. In other words, if this goes to 0, this converges. Why? If this goes to 0, okay. Well, if this goes to 0, then this guy at 1 infinity of AN exists. Why? Because we can show this is Cauchy. Because basically by definition, AN goes to 0 means for any n, everything is less than epsilon. Because we know the strong triangle inequality, so we know the absolute value of AN plus 1 plus this AM. This is basically the difference of your Cauchy sequences, right? This is still less than max of each term, and max of each term is epsilon. So you know this is always Cauchy, and this always converges if that goes to 0, which is very good. And actually, you can do analysis on QP by defining the same logarithm and exponential as is usually defined as a power series. And it doesn't work as well, but it works. It works. Sort of works. You see, the problem is exponential is that n factorial is too large. Like 1 over n factorial is too large. Like this number is much smaller than this. You can tell, right? Like this n factorial on the denominator makes this number too small. This is much smaller because our p-adic norm makes it small and it's large. So the exponential does not converge as well as you expected. It still sort of works. And I don't have time for Hensel's lemma, but I want to talk about ostrosity. Or maybe we could talk about Hensel's lemma. I could mention Hensel's lemma. We can talk about ostrosity theory. So there's a definition. So we define a lot of absolute value or something like that. You realize that those are not all absolute values because you can change, because we define the absolute value of P be P to the negative valuation of P at X. You can also say we can define absolute value by saying that this any constant times negative P. You can verify this is also an absolute value, but they're only off by some sort of exponent. But the definition is if you have two absolute values are equivalent if first absolute value is just second absolute value to the some exponent s. I'm not proving the theorem, I'm just claiming the theorem at this point. I think we are running out of time. And at least I also want to mention Hensel's lemma, and I want to talk why it's useful. We spent like an hour on this like random thing. So I'm just, if you want to check, it's not like a very difficult proof. I think you can understand if you just Google it. The theorem's name is called Ostrowski theorem. Ostrowski's. So this theorem tells you all absolute value on P up to equivalence. It says basically all absolute values up to equivalence are only the P-adic norms and the regular absolute values. And by convention, we just write this as a prime and infinity absolute values. So basically, you can find all absolute value on Q by using this theorem. I'm not proving it; it's not too difficult because I really want to talk about something else. Now I have a definition. So now you know QP is a completion of Q with respect to the absolute value we just defined with P-adic norm. Now it's P-adic absolute value. So now I want to define the ring, the P-adic integers. The P-adic integers. P-adic integers. P-adic integer ZP is defined by definition of the x in QP such that the absolute value of x is less or equal than 1. We also define okay, so you can verify this is a ring. And in fact, you can verify PZP by multiplying everything by P is the unique maximal ideal inside this ring, which makes this ring a DVR, a discrete valuation ring. And you can search out some DVR theories as this is very nice. It's almost as nice as a field, but it's not like it's still a ring, but it's almost very nice. So the definition of so what is P? So PZ is actually a DVR, the discrete valuation ring. What is DVR? The DVR is a local ring. That is PID. So what is PID? It's a principal ideal domain. Every ideal is determined by one single element. If you don't know what I'm saying, you can ignore what I'm saying.
What's a local ring?
A local ring is a ring that has unique maximal ideal.
Okay.
Yes. I mean, you can ignore what I'm saying. You can ignore, but you just know the definition of ZT is this one. And now I want to talk about Hensel's lemma because. So I want to talk about Hensel's lemma because last year I was in the Putnam training and there was a question. It's just Hensel's lemma, and people just say it's Hensel's lemma, and I didn't know what Hensel's lemma was. So I want to talk about Hensel's lemma. So Hensel's lemma says. So Hensel's lemma says, suppose you have a polynomial f that is in ZP, all the coefficient in the P-adic integers. That is monic. Let's say monic. And the hypothesis is f of alpha is congruent to 0 when modulo P. So like integers you can modulo P, but P-adic you can modulo P. Actually, I'll just take a fact here. The fact is ZP modulo PZP is isomorphic to Z modulo PZ, which is regarded as a finite field FP. So we have this guy, and we have f prime. If f prime of alpha is non-zero modulo p, then there's a unique alpha. Let's call it alpha 1. So suppose we have basically supposed to have a polynomial with coefficients in the integer in this p-adic ring, p-adic numbers, and there's a root modulo p, and that root is a single root. So you know multiplicity, the derivative is not zero, it's a simple root. Then we can lift that particular root alpha naught back to f, back to zp, such that f is 0 at alpha, and alpha is congruent to alpha 1 modulo p. So basically what it's saying is, do you guys know Newton's method? It's supposed to have approximated roots. You can keep using derivative to approximate the roots in a computer program. This is pretty much the same idea, but although it's a bit different, but the idea is actually very similar. I just quickly doesn't call the proof idea. But the proof idea is basically going to build a Cauchy sequence from alpha 1. So we want to find alpha 2. So what do we want to prove? Well, we basically want to build a Cauchy sequence, something that looks like alpha n, that tends to something. But because we know it's complete, so Cauchy implies convergence, so we're good. Now what do we want? We want to construct a sequence such that f of a alpha is congruent to 0 modulo p to the n, and alpha plus 1 congruent to alpha not modulo p to the n. So how do we do it? It's actually very easy. We just try to construct something like alpha 2. To make this work, so alpha 2 has to be alpha 1 plus p times something, right? Because we want this to be, they are same modulo p, so we want to kill this, and they are same modulo p. When n equals 1. And now what you do is you expand f of alpha 1 as alpha 2, which is by our definition is f of alpha 1 plus pb. Gonna expand this guy as a Taylor polynomial, as a Taylor series basically. This is actually equal to f of alpha 1 plus p times b times alpha prime of alpha 1 plus b squared terms. So when we modulo the whole thing by p squared, I have f of alpha 2 is equals to f of alpha 1 plus p times b f of prime of alpha 1 modulo mod p squared. Make sense? Because we want this guy vanish at p squared, so we want this to be 0. We also know alpha 1 is 0 mod p by hypothesis, here. So f of alpha is 0 mod p, so we can write f of alpha 1 as p times x. In this way we have what do we have? Px plus p times b times f prime of alpha 1 congruent to 0 mod p squared. We divide by p squared both sides. We divide by p both sides. We have x equals x plus p times b f prime of alpha 1 congruent to 0 modulo p, which reduced to the field at p case basically. Then we remove term. We want to solve b, so b is just negative x, or p is gone here, of f prime of alpha 1. Because this is non-zero, so we can take inverse. So this is the inverse. You take this, whatever, modulo. There we go. It's all b. You just keep going to do the same thing. You can just build a this way. That converts to some number because it's Cauchy, and then you proved Hensel's lemma, which is good. Okay, so I think I'm almost done, but I just want to talk about.
I don't think you have time to talk about anything else.
I want to talk about applications. Just one, at least one. Application. Like otherwise why do we spend an hour on nothing? Right?
For the love of math.
You know, it's math.
With this beautiful
For
lemma.
non-zero score.
Indeed, but I don't think that's actual positive. I just don't believe it. Okay, let's talk about at least one theorem, which is cool. I found. So this theorem is called Hasse-Minkowski. I don't even know the proof, but it's cool. Yeah. So the theorem says let f of x1 up to xn be something like summation of Cij xi x3. Let this guy be a quadratic form. So I hope you guys know what the quadratic form is.
Yeah.
That is just something like x times ax. In the product of x with ax for a symmetrical matrix. Be a quadratic form, and then we say the equation f equals 0. F equals 0. Obviously, 0 is the solution of that quadratic form. But f equals 0 has non-trivial. It's non-zero solution. You can guess if and only if we study a prime at time. If only if f equals 0 has non-zero solution over all p-adic fields QP. P less or equal than infinity, where infinity is R. So this any quadratic form has non-trivial solution if only it has solution all over QP. That's very cool, isn't it? You can study a prime at a time, and it makes your life much easier, actually. I think that's all I want to say. There's another cool theory I want to say. It's called the local conical weather. No, I'm good.
You're good.
I'm good.
Okay.
Let's enjoy.
Anyone have
Any questions? Any?
How do you define some maximal ideal of null sequences or something like that?
Yes.
What is it? Can you explain what that is?
Oh, so that's how you. That's a better way to build a completion without using the crazy Cauchy sequences.
What is a null sequence? I don't know.
Oh, just the sequence tends to 0.
Tends to 0?
Yeah, just any sequence.
Then why does that not generate the same?
Because because you have what?
Why does that not generate the same field as like normal?
Completion?
Normal
It's the same.
It is the same.
But it's nicer if you all use algebra, no?
No, I'm talking about like R.
So R is this infinite sum of Q.
Yeah.
This is your sequences, basically.
Yeah.
Right? And you take I to be all AI such that AI tends to 0.
No idea what
So that's the same thing as QP.
But this is the completion of Q. Q with respect to the norm. This is
Oh, the norm goes to 0.
yeah, like when you say goes to 0, you mean the topology, right?
Okay, yeah. You're so right, Chris.
Indeed. Any
when you say so when those triangles are those in like QP squared or like where are those triangles living? Where they're all isosceles.
QP.
And all like triangles in QP.
Triangles in QP is isosceles.
Okay, but I'm imagining, but like the triangles in R are like dumb, just lines, you know?
Yeah, but like R, you have triangles like lines, you know.
So the triangles you're talking about are just triangles that are just lines. In QP.
Indeed.
Okay.
Indeed, yes.